I'm recording and I have audio. All right. Make sure is that sign-in sheet still going around? Has everybody signed it? Here, pass it on. Yeah. Who has questions from either week's homework? 25. Thank you. Draw approximately the electric field lines at about 2 point charges plus Q and minus 3Q, which are a distance L apart. All right, this is, I showed y'all this. What are the charges? Plus Q and minus 3Q? Plus Q. Minus 3Q. So for this one, we'll start with 6. Works for me. This one is 3 times the charge. So we'd put 18 of these things. All right. Now, because this one is positive, all of the lines are going away, pointing away from it. And because this one's negative, all of them are pointing towards it. Now, we just start connecting those lines. Just like that. Now that one is out of lines. The rest of these just go off into space. Like so. Oh. That way they're L apart, whatever L is. That's how you draw your field lines to give it a visual sense of proportion. You just use the number of field lines as corresponding to the density of or the strength of the field. The density of the flux, if you will. Number of lines per square unit area, whatever. Anybody have questions from any of the other homework problems? 31. Determine the direction and magnitude of the electric field at the point P. In figure 1656. The charges are separated by a distance 2a, and point P is a distance x from the midpoint between the two charges. Okay. Well, this is essentially the same thing you're doing on this lab, which, while I'm at it, while I'm thinking about it, is everyone coming along okay on that lab assignment? Anyone falling behind. All this. And 31 plus Q minus Q and P. X. Okay. All right. We've got to calculate two independent vectors. Well, wait, first of all, what are we calculating? The E field, correct? Wait, what do you mean, and all the different terms? In terms of these variables. Okay, got it. All right. So, let's start with the vector from minus Q. We'll call that one E minus Q. And that will be equal to K times minus Q over X minus A squared. Do you see where I'm getting X minus A? Right? This distance from here to here is the distance X minus A. So it's going to be X minus A squared. Okay? Nope. Well, yeah, it would be X plus A. Right. Now, what's the direction? Of either one. This one, Q, is going to be something pointing in this direction. And minus Q is going to be something pointed in that direction. Okay, but they're both horizontal. Okay, and the sign of the direction is already built into the equation here. So we can, to make these, to account for the direction, we can just make these both vectors by multiplying both of them times the unit vector I. That gives them direction. Okay. So let's see, how can we simplify the top, the minus q? Well, we're going to need to simplify x minus a squared. Can y'all see from over there well? Okay. X minus a squared is equal to x squared minus a times x. Yep. 2 times a x plus a squared. Okay? Now, we square this one out. We get x squared plus 2ax plus a squared. Okay? Now, we got to add both of these together. I've done used up my space over here. So, e minus q plus e plus q equals we've got k times q on both of them. Does everyone see what I did there? I added this term plus this term. And then I factored out k times q from both terms, leaving behind just the 1 over r squared terms. And of course, this is all still times the unit vector I. These are not common denominators, so we can't really add them together directly until we make them. They're not common denominators. We may need to make them a common denominator in order to add them together. And that would be Does anyone have any questions about how I got this? Because I know I kind of skipped over a step or two, but does everyone understand what happened here? Does anyone not understand how I went from this to this? Okay, no problem. No, let's just stop right there. I'll back up and I'll take it in smaller steps. I want to add these together, which means I need common denominators. So I'm going to multiply this one times x plus a squared over over x plus a squared. Because x plus a squared over x plus a squared, anything divided by itself is just 1. So I'm not changing this value by doing this. Now, over here, times x minus a squared over x minus a squared, and that brings me to minus x plus a squared plus x minus a squared all over x minus a squared times x plus a squared. We're good? Okay. So what I'm just going to switch these around. This is x minus a. It would help if I write what I'm actually supposed to write. X minus a squared minus x plus a squared, all divided by x minus a squared times x plus a squared. Well, what's x minus a squared minus x plus a squared? X minus a squared is x squared minus 2ax plus a squared minus x plus a squared, right? So I'm minus x squared minus 2ax minus a squared. Well, now look what happens. X squared minus x squared cancels out. A squared minus a squared cancels out. And I'm left with minus 2ax, which is just minus 4ax. That is the sum of these two quantities. Yep. So my total E field is equal to K times Q times minus 4ax over factor out that minus sign, put it out here, multiply the whole thing by I. I don't know, what would it be? It would be this times this. And that would not make it, if you tried to multiply it out, it would not get simpler, it would get much, much bigger. Because you'd have x squared times x squared is x to the fourth, plus x squared times 2ax would be plus 2a times x cubed, plus x squared times a squared, minus 2ax cubed. So those might cancel out. Are you saying you've done this and it simplifies it? Did anyone do that and find it simpler? Well, let's find it out and see. Maybe it may get simpler. We got that. We got all this over there. Well, let's see if it simplifies any. What are we going to do? We're going to multiply x squared minus 2ax plus a squared times x squared plus 2ax yeah, let's see if we can get there. We square this. We've got x to the fourth plus x times 2ax, so that would be 2ax cubed plus x squared times a squared. Right? Minus 2ax times x squared, which makes that 2ax cubed, minus 2ax times 2ax, so that's minus 4a squared x squared, minus 2ax times a squared, minus 2a cubed x. Yeah, that's I'm looking back, that's x, this x squared times that would be 2ax cubed. Yeah, got it. Okay, and that's up to here. Then I've got to add plus a squared times x squared plus 2a cubed x plus a to the fourth. Okay, here's plus 2a cubed x minus 2a cubed x minus 2ax cubed plus 2ax cubed plus x squared a squared. How did I get rid of, where did that come in? X squared times that a squared. Yeah, and here it matches up here. So that's x to the fourth plus 2 times a squared x squared. That's these two. Let's see. Minus 4a squared x squared plus a to the fourth. Okay, minus 4a squared x squared plus 2a squared x squared is minus 2a squared x squared net plus a to the fourth x to the fourth. And that looks like x squared minus a squared squared. If you factor that out, that's right. It does simplify. So, if you did all of that work and showed it, if you end up with either of these denominators, it's fine by me. How simplified do you need it? But yeah, where it starts getting iffy is if all you do is come up with that answer and then you make me go through all that hard work to prove that you were right, only to find out that all you did was copy the answer in the back of the book. Then I may not grade quite so generously. Yeah. Yep, it does. It simplifies down, but it takes a little doing to get there from here. Point is, That is the total E field at this point based on these 2 point charges. And it is a vector. It's pointing in that direction. So who else? One of the things on the lab. Which one do you want to do? Sure. An electron is released from rest in a uniform electric field and accelerates to the north at a rate of 105 meters per second squared. Find the magnitude and direction of the electric field. Yeah, once again, they're sneaking Physics 1 back in on you. All right. An electron (1.6022 times 10 to the minus 19 coulombs, negative). It is released from rest in a uniform electric field and accelerates to the north at 105 meters per second squared. Find the magnitude and direction of the electric field. Well, first of all, if this is the direction that the electron is accelerated, up, which way is the electric field pointed? Down. Remember, the electron is attracted to a positive and repelled from negative. The negative field points towards itself, positive field points away from itself. So, because this is an electron, a negative charge, it's going in the opposite direction that the electric field is pointing. So our E field direction is south. And we didn't have to break out a calculator to do it. Right. Remember that we say, and it's only by convention, there's nothing empirical about this. It's an arbitrary choice, positive and negative. But we say that the electric field points away from the proton, away from the positive, and points towards the negative. So when you're drawing your point charges, minus Q has the E field lines pointing towards it. Positive Q has them pointed away. Right? So if you take a loose electron, and you set it here, it's going to be repelled away from this negative charge and towards the positive charge. Okay? Another way of looking at it is we say the direction that the E field points is the direction it's going to push a positive charge. Therefore, if you have a negative charge, that charge will be pushed in the opposite direction. And this really is, it's hard for everyone because it's arbitrary. Yeah, it's Ben Franklin. Ben Franklin was the one who decided that. Then that would be a plus, and it would be pushed in the same direction as the field. So it would be accelerated to the south instead of to the north, because it would be pushed in the opposite direction of the electron. Okay. Now, if you want to go all the way back, full circle around, if we start off by saying it's a proton and it's accelerated north, then which direction is the E field? It would be pointed north, because that's the direction it's going to push a positive charge. The E field will push the proton in the same direction. It will push an electron in the opposite direction. Exactly. This one's, the electron's going north, so the E field is pointing south. And it's pushing the electron in the opposite direction. Now, that might be a little bit confusing, but that's all there is to figuring that out. What's the other part of the question? The part that's not so simple. That's the acceleration. Now, here is another time where it really matters whether you're talking about an electron or a proton. Mass of an electron is 9.11 times 10 to the minus 31 kilograms. What's the mass of a proton? It's minus 27. Proton rest mass, 1.67 times 10 to the minus 27 kilograms. That's the mass of a proton. These would be very handy things to have written on your index card. So, what do we know from Physics 1? Newton's first law, motion. Force equals mass times acceleration. In this case, someone with a calculator, give me the numbers. 9.11 times 10 to the minus 31 kilograms times 105 meters per second squared. Call that out again. Times 10 to the negative 29 newtons. That's the force that this electron is experiencing. Coulomb's law tells us that that force is equal to K. Nope. Is equal to E times Q. The electric field times the charge of the point charge. So we can rewrite that equation as 9.57 times 10 to the minus 29 newtons is equal to E times 1.6022 times 10 to the minus 19 coulombs. And if we divide both sides by that, we get what did it come out to? Newtons per coulomb. Did you get that answer? Q times E over M. Right. That's what I just did. See, what they're saying is, we're saying force equals mass times acceleration, which is equal to the electric field times Q. So if we take MA over Q, that leaves us with E. That's all I did. I just showed you where it came from. That we started off with Newton's first law of motion. Yeah, I did not do the arithmetic. If this is wrong, blame him. Somebody else confirm that it works. Okay. Okay. That happens more often than I care to mention. Especially, boy, I hate these stupid little smartphones with those little made for girls with the skinny needle-like fingertips. Virtual keyboards, I can't stand them. Okay. We have looked at how we got the E field. We looked at electric fields and how they interact with conductors and conductive surfaces. We also need to cover Gauss's law. So I'm sorry about getting if we have time, we'll work one of the vectors from your lab. Is there one in particular that's giving you trouble, or you just need a refresher in how to do it? Okay. If we run out of time in class, then come to my office and I'll work through one of them with you again. Gauss's law. What's his real name? Friedrich Gauss? Is that it? Carl Friedrich Gauss. Even sounds German, doesn't he? Oh, yep. Everything you say in German, it just sounds mean. It just sounds mean. There's a reason they're not called the Romance languages. Yeah, that's the other side of that coin. If you learn to say it in French or Italian or maybe even Spanish, it doesn't matter what you're saying. It just sounds like you're being nice. All right. Carl Friedrich Gauss. He came up with this formula. And I'm just going to start with this concept of flux. Now what is that expression? What is that saying? You want to, in fact, if you want to follow along, I'm on page 463 in the book. Right, but the area, the flux, density, the amount of the E field that is passing through this plane varies with angle. Okay, and I will try to draw this as best I can. Say this is a uniform electric field, and we've got a square of area right here that's perpendicular to that E field. Now, I see how they drew this. Let me try again. It is. Got your E field. Now, in this E field, we have area of plane. Okay? And this vector that is perfectly perpendicular, that's normal to that plane, comes right out of the center of it. Okay? Basically, I'm looking at this. There's your plane with the vector coming right out of the center of it, normal to it. This vector forms an angle with that electric field. Now, right now, that angle is 0 because it's perfectly parallel to that electric flux field, that E field. And that means when this angle is 0, cosine of 0 is equal to 1, and the flux is the amount of area, is the electric field times the amount of area that you've got covered. Now, this is, of course, assuming that it's a uniform electric field. Okay, if it's varying, then this won't hold true. We're not getting into that level of mathematics. Okay, we're gonna do Gauss's law as simply as we possibly can. Now picture this frame this unit of area being rotated. So inside this this electric field, now this vector normal to that surface is at an angle theta. Well, as theta goes from 0 towards 90 degrees, cosine theta gets smaller and smaller until you get this thing turned flat, so the vector is pointing up perpendicular at 90 degrees to the E field. Well, at that point, it's easy to visualize that if this is your vector field, this is your E field, and your unit of area is parallel. If your area is parallel to the E field, the vector normal to it is perpendicular to the E field. How much of that E field is passing through that plane, that unit of area? None. So when this goes to cosine of 90 degrees, it becomes a 0, and the flux passing through that unit area is now 0. Another way to envision this, although this gets really, is at this point you have an E field vector. And that E field vector is basically comprised of two components. The part that's parallel to the plane here, and the part that's perpendicular to the plane. E perpendicular. The component of that E field vector that is parallel to the plane does not pass through it. Only the component of that E field vector that is perpendicular to the plane is the only part of that E field that passes through that plane. Okay? Somebody help me out. Do you understand this? Or have I completely confused you? The pictures in the book are a lot better than I can draw, okay? But this is the part that is the most crucial. So let me try and see if I can draw this. Simply, no, I'm not going to erase that. I'll just do it over here. Let's see if I can try and draw this in a simplified version. We're going to look at it from the edge. I'm not going to try and draw a two-dimensional plane and rotate it and all that. Let's say this is our plane of unit area looked at from the edge. Okay? This is our E field passing through it. Okay? Well, actually, this is the E field. So, if we break this down, this E field vector has this component parallel to the plane. That parallel component of that E vector, that E field vector, is not passing through this unit plane. It's parallel, it's not passing through it. If we take this part perpendicular to the plane, this component of our E field is the part that's actually passing through the plane. Okay? So, if the plane is perfectly perpendicular to the E field, then all of the E field is passing through that unit area. But as you rotate it, less and less of that vector is passing through it, and more of it is being lost as parallel to it, until you get rotated through 90 degrees, and then the whole field, the whole vector, the whole E field is parallel to the plane, and none of it is perpendicular, and none of it is passing through. The normal vector, yeah. Yeah, this is your plane. You can visualize it that way if it helps. Then it's like just lines that pass through that plane. And the more you turn it, the less and less of those lines are passing through until you get it turned all the way flat, and then none of them are. Okay. This is the crucial concept that you need to get your mind wrapped around in order to understand Gauss's law. If you take an E field and you construct a closed surface around any portion of that E field, okay? This doesn't mean an actual physical surface. This means this is a mathematical construct. In fact, it's called a Gaussian surface. It's just an imaginary surface that doesn't physically exist. It's just the surface over which you are going to sum or integrate all of those little perpendicular components of E field. Okay? You construct that surface. Doesn't matter how you construct it, however is convenient, but you construct a closed surface. That's the important part. It has to be closed, fully enclosing a portion of E field. Then you go over that entire surface, and every little infinitesimally tiny piece of area of that surface, you multiply that little infinitesimal piece of area times the component of the E field that's perpendicular to it at that point. And then you add up all of those little products of pieces of area times perpendicular E field. And as you add them up all over the whole field, the whole surface, they're going to total up to the charge enclosed by that surface divided by epsilon sub naught. For the moment, epsilon sub naught is just a number. It doesn't matter. It's a constant number. We'll get to it later. Don't get caught up on that. The important part here is this. The charge enclosed inside your make-believe surface, your Gaussian surface. Now, how is this written out? He writes it as, the book writes it out as the summation over a closed surface of the perpendicular component of electric field times the small increments of area will equal the charge enclosed divided by epsilon sub naught. That is Gauss's law. Spent too much time on problems and didn't get to the lecture again. What you do need to know about this is epsilon sub naught. It's 1 over 4 pi times k. And the book does a pretty good job of walking you through how to use Gauss's law. .38. Let's do that one very quickly. That's the Gauss's law one. So, what do we have for 38? Total electric flux from a cubical box of side 28 centimeters is 1.85 times 10 to the 3 Newton meter squared per Coulomb. .28 centimeters, 28 centimeters, 28 centimeters. Now, what does Gauss's law tell us? If we add up 1, 2, 3, 4, 5, 6 sides of 28 square centimeters, if we sum over all of those, that's going to equal what? Q enclosed divided by epsilon sub naught. Now, what is the sum of the areas on this? 28 centimeters is what? 0.28 meters, right? So it's 0.28 meters cubed. Nope, sorry, it's not either, is it? It's 0.28 meters squared times 6. What's 0.28 squared? .074? 0.0784? Wait, 0.0784 or 0.784? Good enough. And then multiply that times 6. 0.4704 square meters. That's our total area if we add up all of the delta areas. And we know that the total flux emanating from it is what? .85 times 10 what? That's our flux. And It's times 0.4704 gives us what? You understand what we're doing here? We're taking the total flux coming out of that whole surface times the area of the surface. 870.24 what? Yeah, the units. What does that equal to, though? Epsilon sub naught. And epsilon sub naught is K times 4 pi is equal to 1 over epsilon sub naught. Or epsilon sub naught is equal to 1 over 4 pi k. In this case, why don't we just multiply k times 4 pi times q enclosed. Get rid of some of this other stuff. And now we can solve for q enclosed by dividing 870, and I'm trusting someone else for the arithmetic, divided by k is 9 times 10 to the 9 times 4 pi. That's q enclosed. So punch the numbers and turn in your homework. Everybody did sign the sign-in sheet, correct? What you're going to discover in the course of this semester is that Gauss's law, while it is useful in very specialized, simple situations for our purposes, in order for it to be in order for you to actually fully appreciate the utility of it, you'd really have to get into some more arbitrary and calculus-based physics. All right. One exam. One exam. One exam. Got your homework? Oh, got it. Thank you. One exam. Pass this over to Cyrus. Dalton? Yeah. There you go. You bet. Merci beaucoup. Is that, oh, you're still working on, that's your lab homework. You want to come by the office and I'll walk you through one of them? Give you a refresher on it? All right.